Okay, so this is the last part of the chapter 6. So in the last class, so chapter 6 is about finding the optimal regime, right? So some literature, the regime is called the policy. So sometimes it is called the policy search or something. Why? What's going on? I think something's not real. Okay. Anyway. So value search method. So to find the optimal policy or optimal regime, we studied Q learning, right? Q learning and A learning. So that's the what we covered the last class. So that these two essentially is based on the sufficient condition, right? So the one of the main result is that the optimum the sufficient condition is that the optimum is conditional expectation. So arg max A of the Q XA, right? Remember? So okay. So if basically this guy in the single case, so arg max A. So if you choose this one, this particular one satisfies the optimal, right? Is optimal. So this Q learning and A learning is about how to find this surface the condition. Now today the value search, it doesn't really use this surface the condition. Rather, it uses the definition directly, right? So we want to use an unbiased estimator of the value function and then try to maximize in the parametric class. So you should have a parametric class of the a policy or a regime, and then try to optimize among that class. So the first one, step one, is the consider class of the decision rule, and then second step is estimate the value in terms of the parameter, and then try to optimize the value. So estimate the value with respect to eta. So that is basically the idea. But now, unlike the single, so this is a kind of single DTR result. Here we are talking about the multiple, right? So multiple treatment regime. So that we need to use some sort of the sequential backward induction on top of this value search. So the idea of the value search has already introduced in the single DTR case before in chapter 4, but now we are going to apply to the multiple step, right? Multiple treatment regime, multiple K case. So, okay. So now the problem now reduces to how to compute the unbiased estimator. So unbiased estimator of the value function, value for a given D. So we'll first introduce the IPW approach first, and then move on to the augmented IPW approach. So the IPW approach start with defining the regime consistency indicator function, right? So the regime consistency indicator function is essentially, so given the policy, we want to check whether the current data current observation satisfies this condition, satisfies the so realized value. So basically, the realized value of A matches with the best the policy that under the matches with the choice under the given policy, right? Choice of the options in the given policy function. So then to apply the IPW estimator, we need to compute the conditional expectation of delta given the data, right? Given the history. So in order to compute the conditional expectation of delta, we need to first use the propensity score model. So this is the propensity score model, which is expressed in terms of the potential outcome. But then this one can be equivalently written as a function of the observed data. So that this is a kind of identification result, right? So we kind of see that several times before, but I just so do it again. So basically, what matters is whether how we want to express. So we want to show this equivalence. So the user tip is to start with the complex one and then try to simplify. So start from the from this one to show this one. Okay. So that is this one. And then we can use base. So it's a kind of we have exactly the same structure of the proof that we showed before, right? So if you recall this proof, let's quickly check this one. So chapter 6, part 1, equation 6. Chapter 6, part equation 6. Yeah. So what is the equation 6? Equation 6 is basically the showing the conditional expectation, equivalence of this conditional expectation, where the first one is in terms of the potential outcome, while the second one is in terms of the observed data, right? So basically, this is another version of the identification result, because this is what we are. So the basic idea is the quantity of interest, right? The quantity of interest is defined through potential outcome, right? So that is a kind of a causal parameter, right? Causal parameter that we are interested in. But since the causal parameter, since the causal parameter is defined in terms of the potential outcomes, we cannot really observe that, right? Observe them. So the idea of identification is to equivalently find the equivalent expression in terms of the observed data. So that is the key identification process, right? So we are kind of doing the same thing, exactly the same thing, in terms of the A, right? So this given part is the same. So this part is the same. The only thing is different is this part. So that is basically, basically this one, right? So basically this one. So basically, with this given part is the same as before, but this guy is now about the probability of A. And then the structure of the proof should be the same. The structure of proof is essentially using the Bayes' theorem and then apply the Sutuba. By the way, if the Sutuba is a term proposed by Rubin, but it's nothing, right? It's just consistency. And James Robbins is not really good friend of Rubin, and so in James Robbins he never uses the terminology. Just to say, so we can just call it consistency, right? So measurement consistency. Basically, what you measure. So what you observe, right? What you observe. I'm sorry. What you observe, right? What you observe is a function of the. I mean, something like that, right? Indicator. I mean, to be rigorous. So your observation. And so, what if you know the potential outcome and the choice, then you should know the observation, which is essentially consistency, measurement consistency. There's no extra additional noise. So anyway, so that is the second equality, and third equality is again base, right? And then last equality is that we conditional independence. So AK minus 1 is conditional independent of the potential outcome. I should, okay. So I guess AK minus 1 is conditional independent of the potential outcomes given the older people, right? I mean, K minus 1 history, given the history, essentially. Okay. And then once you prove this, then you can basically check this relationship and see that all we did is just sequentially express the x bar xk random variable xk, this one. So xk, right, as a xk x star k, and then the a, it becomes a the time is a step backward, and then you apply recursively, then you can get all the way to this. Okay. Okay. So now once you so now we have this propensity score function and the regime consistency function. Then we are now in a position to define the IPW estimator. So IPW estimator is a regime consistency indicator divided by its corresponding probability, and the corresponding probability is basically derived using the propensity score function for the A. So this is the AK equal to AK, right? Given the history, given let me see, isn't K minus 1, right? Yeah, sorry. So I think I kind of messed up somehow. Why? I don't understand why, but it should be a K minus 1. Huh? No?
And the other one, A bar is one, right?
I see. You mean this one is actually a k plus 1 equal to a k? Is that what you're saying?
It's five. It's birthday.
X bar k, okay. But my point is, so something's not really correct. X bar, because xk itself is the function of the choice of ak, right? So you cannot really, I think this is not really, you know what I mean? Sorry, I should have checked it more carefully, but this one, right? This is APW. So this one. This is strict. No, this is a learning. Okay.
There should be another A bar minus 1, right?
I see. So this is actually, I see. Oh, sorry, I was, so nothing wrong. Okay. I see. So AK depends on XK. So basically, AK is determined using the XK. So it's not really nothing wrong. I mean, so the probability of this, so the point is you can multiply, and each one basically, so this probability is equal to this probability. Okay, so this probability of, so what is the conditional probability of the right?
That, so in that equation, there should be A bar k minus 1, right? 5k, X bar k, A bar k minus 1. This should be the history. X bar k, A bar k minus 1. Or you can use A bar.
So suppose k equal 2, right? Then you have a1 and a2. So x1, basically x1 is used to x1 used to a1, and a1 is to make the x2, and x2 is used to, so this is like this, right? So a1 depends on x1, and x2 depends on a1, and then so something like that. So y depends on a2. So then AK should depends on x bar k, right? So that's no problem. So I don't know. Is that okay now? Okay. Okay. So basically, and then for this one, for this event, we can use this as a probability. I mean this one. This one is used as a probability. Because we can use x to obtain decay, and so that we can use this indicator to find a right propensity score function.
What's your definition for pi k?
So pi k is this one.
Okay, understood.
Right. Okay. And then conceptually, once you have this estimator, then you can write it as a function of the eta parameter eta, and then you maximize find optimization, maximize over eta to obtain eta hat opt, and then plug in to your so this guy is plug in here, this guy is plug in here to obtain the optimal policy. But as this is inefficient, as it uses only those cases with a delta equal to 1. So that is just the beginning, but we need to improve it further using augmentation idea. So the augmented IPW estimator uses the start with the IPW estimator, but now you use partial information. So the partial information that we're going to use is that for the sample, X1 is observed. And delta equal to 1, we observe X1 and X2, right? So that is the, basically we use a monotone missingness idea. And then the optimal choice of, using this, semi-parametric efficiency theory on the monotone missing data, we can actually obtain this one as an optimal efficient IPW estimator, right? So that is the solution, known solution for the case of the optimal monotone missing. So the problem is, so we already know how to compute this one, right? We already know how to compute the pi. So now we are in a position to compute the conditional expectation. Then we can, using that, we can compute the IPW, AIPW estimator.
In the resource method, so you're considering a class of decision groups, right?
I'm sorry?
You're considering a class of decision groups.
Yeah, eta. So this is the for eta, d eta, right? So this is the parametric class, some kind of parametric class of the decision rules that we have. So we want to view it as a function of eta, and optimize over eta. So that is the. Huh? I'm sorry. So okay, so in the beginning, so the Q learning, A learning, we studied, yes, I mean last class. So the material here uses the sufficient condition, and now value search is a third method. So this is first method, second method, third method.
My point is, which method is good? Like,
Huh?
which method is good?
No, this
Then
there's no uniform. I mean, this is for the particular. Actually, this is, if I know Q function, then this is already good. So this is the best. But Q function is requires assumption, right? The model assumption.
But even you know Q function, that does not give you the best one.
No, best. That is a theory.
But it didn't use like the selection model.
No, this, well, okay.
Q learning is just outcome model, right? So only use the outcome model.
Yeah, if the model is true, then it's the best. The A learning is a semi-parametric model approach. So it gives a more robust estimation. But the theory itself, I mean, if you really believe so it's like if you know the regression model is true, missing data, then you can just do regression imputation. You don't have to do augmented whatever. That is only for the protection, right?
Okay, so So only use the outcome model we can achieve the efficiency.
Yeah.
Because we have asked, I mean, the outcome is independent of the response. So we can, if we exactly know the form of Q function, then we can estimate them separately without giving the response number.
So this is the main result. So this, if I know this, then this one satisfies this.
Yeah. That is the optimal
Right.
given you know the true Q.
Q, right?
Yeah, but the estimation of the Q only based on the outcome model is not the most efficient one. Because you have missing data.
Well, under the no. So are you? But we are assuming the model, outcome model.
But there are unknown parameters involved.
But we have identification condition already.
Right, but I'm saying you only use outcome model to estimate. Okay, I see. So because this is essentially the regression problem.
Right. That's exactly true.
It's not the estimation problem for the response. It's just
Right.
the regression problem.
Right. This is essentially regression problem, right? So, yeah. So if you like in the missing data, if you really believe that the regression model is true, then the linear regression is the best. Yeah.
But that estimation of response is not optimal if you only use the outcome.
Okay. Huh? So optimal decision. Okay, optimal decision uses. So, I mean, this is the main result we are using. So this is using this property is Q learning or L learning. And this one is actually using the definition directly. Okay. Yeah. Okay. So the theory for monotone. So basically, if you introduce this regime consistency indicator, it becomes a monotone missing data problem. And so the optimality here is derived using the monotone missing is theory. Okay. So so we already have this result, right? So this is the if you have a model, then we can use it to estimate Q function and then apply to the AIPW estimator. So then question is how to compute this Q, conditional expectation for. So we can think of two approaches. One is the G computation approach, which is I'm going to introduce soon. Another approach is a kind of backward recursive estimation approach. Yeah, so the book somehow, the lecture note is somehow repeating the same concept, but making a little bit more, generalized soon. So that's for some it's actually nice, but in some sense it's confusing, right? So basically this is kind of we already the concept already we studied, but anyway. So here, what do we mean by G computation? So basically, G computation is essentially a tool utilizing the identification condition. So we can, as long as you can, factorize, right? Factorize the conditional distribution, then you know how to estimate each component from the observed data. So that is basically the idea. So in other words, originally the problem is a potential outcome, right? Regression model. So this is the original problem is a potential outcome regression model. which we don't observe, right? We don't observe these potential outcomes, but we do observe one particular realization of the potential outcomes. So it is actually the movie Everywhere. I mean, so it's really about multiverse. This is actually multiverse. So if you have a single population, it's a universe, right? But it is a multiverse, depends on your choice. So, but interesting part, we know that which A it came from. So that means we know which universe it came from, right? So that we can at least, locally, right, estimate the conditional component from the observed data. So, so originally the problem was like a potential outcome, but end of the day we can make the model specification using the model parameter. So the difference is, you can see that the difference here is that you conditional on the potential outcome under the particular regime, right? Under the particular policy or particular option, you can actually have a realized X with the corresponding the realized, right, A value, so that you know which X star it is referring to, right? So here is potential outcomes under the particular choice of the D, right? But they are all basically 0, 1, right? I mean the options. So then from the data, as long as you have the realize that observe the data from that particular path of the choices, then you can basically estimate them using the maximizing the partial likelihood. So this is the basically you can see that this is, so here k equal 2, this is nothing but the conditional probability of the x2 given x1, and so yeah, it's so x1 a1, x2 a2 y, right? So if you use this map, that means what? You can actually estimate the conditional distribution of x2 given x1 and a1, right? So which is this one? So same story here. Conditional expectation of the y given x1, x2, a1, a2. So you can get this, right? So that's this one. So you should be able to. So the basic idea of G computation is that you can identify the conditional distributions, and then once you obtain the parameter, then you can basically identify all the conditional distributions so that you can estimate all the conditional distributions, and then you can essentially, you are now in a position to compute this causal potential outcome parameter, potential outcome regression model, because you know everything, right? So for example, here, whatever D1 and D2, you can compute, use this probability, so that you can basically, so this one you can compute from the beta 2, right? Beta 2 hat, and then this one you can use beta hat 1, and then compute. So this one will involve some Monte Carlo computation, but the concept should be clear. And then remember, so in this example, we need two versions of the conditional expectation. One is the y star given x1. The other one is y star given x1 and x2 star, right? So So that is basically this one. Y star given x1 and y star given x1 and x2 star. Okay. So second one is easier because it's you just use the beta hat 2, but the first one needs additional model to integrate out. Okay, that is the G computation. So that's quite involved because you need to compute all this even for k equal 2, quite involved, but should be as long as your models are correctly specified, right? As long as your models are all correct, that should be efficient, achieves the most optimality. Okay, and then alternative approach is to so here you can see, so you want to see, so here basically how can we compute, so it kind of average over x2, right? X2 star, right? How can you compute this condition expectation averaging over the x2, so that you can do basically using recursive backward. So basically here you define, so now outcome variable is this star, y star, and then conditional on, what you are conditional on is just the observation up to k. Okay. So it could be k equal 1, then you are conditional on x1 only. K equal 2, you condition on x1 and x2, something like that. So then if you use this definition, then you will get this property, right? So basically conditional on y star given x1 is a conditional expectation of the conditional expectation of y given x1 and x2, conditional on x1, right? So that is basically this property. And then now it's the same problem. So now the question is how you can express so this is a potential outcome function, right? Potential outcome regression problem. And now you want to translate it to in terms of the observed data. So for capital K, no problem, right? So for the last one, which is basically this is y star given all the x stars. So that we know this result already. And second term, this is the first equality here is just this one, right? Is this one. Second part is identification, right? You want to express the potential outcome is conditional expectation relationship as a function of the observed data, which we already proved. so that is a kind of we proved before. So now we're gonna just accept. I'm not going to prove it again, but we did a similar thing before, right? So basically the conditional on potential outcome should be equivalent to written as a conditional on your observed data with the choice corresponding to the given potential outcome. I mean, given the D, whatever the D. Okay. So now, the basic idea is So I guess so we want to use this relationship to do the regression. So we use this case only to estimate, because this one, right? Because here this D, I guess this D is actually for the whole sequence K, and this is the up to K minus 1, right? So when we compute this conditional expectation here, this should be a consistent subset of this D, right? Otherwise, it doesn't make sense, right? So basically, that means when you are doing this kind of a backward type, so now we're gonna do backward induction. So you start with the capital K regression and then move backward. So which means we're gonna use the regime consistent cases only to fit the regression and to estimate beta K. And then use that and then construct the pseudo value, right? Pseudo outcome. And then basically use regression of this guy onto, so regression of this guy on X bar using the constant cases. So that's basically we use this as a pseudo outcome variable. So pseudo outcome is what? Essentially if you look at this guy is eventually Y star, right? So that this guy is a, so if you observe, okay, if you observe Y star D, then no problem. But because this is only given, so we need to basically carry backward. I will come back to this point again soon. Yeah.
For those two approaches, so I'm trying to think. So this one is kind of doing this recursively.
Right,
So,
backward, right.
Yeah, so the next step estimates based on the previous step estimation and based on
Right.
So then it's very difficult to do analysis on the estimation of the pattern because it depends on the previous.
Okay.
Yeah, and the different one previous. Then why people prefer this one over the other approach? The other approach kind of like doing all those parallelly, right?
Okay. Yeah, that is a good question. Actually, let me go all the way to is actually. So here's some example. So it's kind of understanding what's going on with Q learning and all this. Suppose I have two, K equal 2. So, and I have data, right? So how you want to do Q learning and things like that? K equal 2, right? The last step, no problem, right? You just feed, you use all the data and feed the regressions using the standard regression, right? Apply the standard regression and obtain Q hat, right? So you could use parametric model if you believe the parametric model, but if you don't believe parametric model, then you can just do the regular lasso whatever, right? So that's Q learning. Okay. What is the value search estimation? It's similar, but the fundamental difference is that you compute the value function. So what is the value function? So value function, I'm not value function, sorry, value of the d eta, right? D2 eta. So which is D2 here, actually this guy. So D2 is a function of H2 and then eta, right? Eta 2. So how can you compute this using Q if you estimate the Q? Well, you just, because you already know the conditional expectation, so you can basically compute the Q, right? Q2 using evaluated at H2I, which is this one, right? So my point is that if you have 1 over n here, this guy is equal to this, right? So that is clear. So the difference, slight difference, is that the Q learning actually estimate the Q function. I mean, it's use the function directly, while the value search uses the value, estimated value, and then find parametric MLE, I mean, like MLE type estimator, and then plug in to obtain the function. So they are different, right? But very similar in terms of the using the model. I mean, regression model. So
Even the value search should also use the response model.
this one Q to head. So we are using the same Q to head, same.
So the value search didn't use the selection for this example.
No, either Q learning. I mean, we are talking about the regression based, right? So this is a regression based approach. So under the regression, basically we use the regression. We use Q function. We learn Q function and then use it to find the optimal decision, either by directly using the maximizer or use the value. Okay, so now
And you're keeping the system is working as a parameter, right?
I'm sorry.
It's in the Q learning, because we are trying to get the maximum in terms of rating.
So this is a function of x. So this is a kind of non-parametric, becomes a non-parametric, right? But here you have a parametric model already. So yeah, this is a kind of a black box type. If you use machine learning to obtain this Q function, you will get very black box decision rule, right? And how to interpret. But here you have a very some kind of parametric rule, right? So if you are just interested in determining the threshold for the rule, then this is better approach. Okay.
So what is eta? Eta 2 is a parameter of E, or eta 2 is A2?
Huh? No. This is a parameter.
The first one, there is
So your rule could be, for example, if CD, what is CD4?
The one
Is
maximize
eta 1.
the value function is like MLE, the estimates of eta 2.
Okay, let's go back all the way. So yeah, this is the starting point of the discussion. Is we wish to find so the value search. So this is the description of the value search method. You have a class of decision rules in the beginning, and your problem is to find eta.
it is like a parameter.
Eta is parameter, right?
So I think this value search means that we have a predetermined parameterized zero rule, and we are trying to find appropriate parameter to help us do best.
Exactly. Right.
best Q, find what kind of E
Right.
achieve the optimal Q.
Right. So really, this is a kind of a doctor's rule. I mean, so this is we are talking about the
So the eta is not the parameter of the Q, because if we're talking about the parameter of the Q function, we need to estimate the parameter based on the data.
so we are talking about the interpretable dynamic differential regime. So interpretable means the decision rule has some data and history and the parameter. And so this is data, right? The history of the, and then this is unknown. And so, the authors argue that there is a good reason to use this one. Suppose this is kind of a given, and then all we care about is how to determine eta. So that is a kind of a problem in their precision medicine practice.
Is good, then I can choose the which treatment I need to give a patient.
Right.
Which like this ratio.
I mean, this is pretty much subject matter knowledge, right? Subject matter knowledge actually knows which variable is important and how you want to use, right? You have a nice function already. And all you don't know, so what you don't know is the particular parameter that so this is because that way you can do some interpretable decision, and that uses the domain knowledge. Okay, so my point is, so that's not really my point. So this is so this decision 2 is actually easy. So my point is, what is the decision 1? So decision 1, basically, you want to do the same Q learning. So Q learning is just a regression, right? So you want to do regression, but you want to do regression of what? Regression under the Y that you would obtain on the T2 optimal. So that is a very important. So you are not really interested in the observed Y. What you're interested in is your Y star as a function of A1, and then you care about this one. So this one is already. So this one is already determined from decision 2, right? And so you plug in, then this one is what? That is actually interesting because you know individual has a Y, right? You individual has a YI, and then individual has a A2I already. So this A2I could be different from this one. So what do you want to do? Well, so the pseudo outcome could be two things. One way is to do prediction. So Q2. So this is one way. Q2, H2I, and then eta hat. Not eta hat. Sorry. D2 OPT. So this is one possible way, which is basically what? That is actually conditional expectation of Y star on the of A1 and T2 hat OPT A1. Basically H1, H2I. Given, so what is Q2H? Q2H2 is you have a history, right? You have a realized one. but you want to replace it by the optimal decision rule. So that is H2, right? My point is that, so this could be one way. So that is what we covered when we studied Q-learning. But another way is you can actually, so it's like a regression imputation. If you view this way, this is just a regression imputation, right? You just a regression prediction of under the optimal decision. Now, another way is actually you can use regression imputation. So you can use regression imputation plus the residual on the data, under the observed data, right? So this one is expectation under your optimal choice. But this one is what? The residual that you realize the residual. So if you do that, basically this one reflects the variability. So we are kind of, so this is a regression implication. This is more like a regression plus residual, hot-tech residual imputation. So some literature uses this one, but some literature uses. But I think this one, there must be some advantage of using this one, because this one is kind of over smoothing, right? You use predicted value to learn another regression function. That seems to be a little bit, over smoothing. But this one actually has a variability in it, so supposed to give a better estimation of the better learning for Q1. Okay. So my point is, pseudo outcome is nothing but the imputation, right? Nothing but the imputation, but the imputation on the different universe. So my current universe is this one, right? But I know the best decision was actually another D2, right? D2 optimal. So this is another me in another universe. So it's really, you have a different universe, and then this universe is where I live in, right? This is the where I live, essentially. But this is another universe, right? Under the so if I chose that decision, right, then this could be a new imputation. Okay. Well, let's so that is the kind of idea behind. The bottom line is we can apply delta to construct the IPW, and then use Q-learning to compute the Q function. But when you compute the Q function, the last observation is relatively easy, because it uses basically you use the realized observation, right? The whole data. But this one, this one is actually based on the optimal. So I should, sorry for the going back and forth. And so this is actually what I want to say. So decision 2, at decision 2, this is my value function, estimated value to optimize. So then we can use this as an objective function to optimize. And then once you obtain T2 hat, then my Q1 will be the potential outcome of the Y star on the T2 optimal. And that requires some innovative imputation because it's not really from the using the current data, but for the another universe imputation using the another universe because I know I should go use this one, but I use something else, right? I chose something else. So that gives us some difference. But anyway, sorry about going back and forth. Let's just go back to where we were and then move on. So the bottom line is we want to estimate the value of a particular policy or a particular decision rule. And that's a very difficult problem if you have a non-parametric decision rule, right? Because you cannot really compare. But if you know the particular class of the decision rule, then there's some hope, right? You know the functional parametric form. So here's the summary. Okay, right. So bottom line is that the implementation by direct global maximization of the value, estimate value, in terms of eta, may be infeasible in practice due to its computational burden. Because for each one, so I guess to answer Yumo's question, we have two approaches, but this is for given D. Okay, so for given single D, these two methods has a different computational, time or burden. So the first one is much more difficult. I mean, heavy in terms of computation, because you need to do Monte Carlo simulation, right? Monte Carlo computation for given D. And then you want to compare it over different D, then you need to reevaluate. But the book kind of claim, I kind of agree that the second approach does not have to recompute your regression. It uses the same beta hat, but I don't know exactly, but I think I'm not sorry. I will back up. But at least it's not really involving the Monte Carlo. So because this one uses the consensus measurement. So if D changes, then the delta will change, right? D changes, delta will change, so that the regression will have to be changed. I guess estimated regression will have to be changed. So it still has to recompute for every different D, but nonetheless, this is computation burden is less.
So now I kind of say the reason is so the first approach basically is very challenging to do the maximization.
Okay.
Yeah, because the first approach you gave them D1 and D2, right? And they can do the first approach, the estimate the beta and then evaluate the value function. But the maximization over D1, D2 will be difficult. And the second approach kind of give a pass.
Right.
Do the maximization. So
that's right.
Like a recursive.
Because you were right.
Give a pass.
Right. Okay. So, and then right. Okay. And now, here's so this recursive approach is actually a simpler approach in terms of computation now, because the point is that the previous two approach here uses the joint maximization. Okay, so this one is a kind of a finding the joint, but here the recursive approach uses the backward induction idea. So basically it resembles the backward induction because you basically want to first determine eta k and then eta k minus 1 or something. So want to do it backward. So then for this recursive approach, they have three methods. So they are all the Davidian NC state group. So they basically, factory. They did they made a factory of the papers on DTR and work with Zhang and Zhang and Zhao and all. See, yes. Huh?
She's from maybe Canada. So she also.
Yeah. So yeah, I think it's start from a very small group, but it's kind of exploding a little bit. But still, here the key person is Mary Davidian and Chatis. They are couple, right? And then Labor is a student or postdoc, and this guy is also very famous at Duke or UNC something.
Yeah.
It's
Yeah, but he probably changed his position.
I see.
Yeah, and Zheng Tongmin is also professor in IC.
I see. Okay, I see. So anyway, so they kind of imagine all possible combination, right, over the method, and then write up paper for every possible combination. So basically, for the recursive approach, you can use IPW estimator of the value as IPW estimator, AIPW estimator, regression-based estimator over the value. Okay, let's see what's going on. So what I mean by backward recursive implementation. So this is the same thing, right? Same expression, but now the key idea is if delta equal to 1. So we only care about delta equal to 1 case. So if delta equal to 1, then A1 is equal to D1 and AK is equal to TK, right? So we have this consistency. So if you compare this equation 2 with the equation 6, so equation 2, the numerator looks the same, right? But the denominator, the way we express the probability of the particular regime, right? So there's the consistency probability can be written in terms of the history and A. So see here, this is as a function of D, right? So here in equation 2, it was written as a function of D, but if you look at equation 6 now, it's written as a function of A. So that is the main difference. Okay. And it's okay because for delta equal to 1, A is equal to K, D, right? So because we only care about delta equal to 1, A equals D, dk. So that's why we can write this way. And then when we write, so the denominator is the dependence on d eta, right? Dependence on eta disappears in the denominator, and only the numerator. Okay, and then once you write it, and then so this is becomes a single decision. So once you write, so this is different, right? So this is the IPW estimator of the value, which is the exponential expected. So this one estimate the expected of y star given d eta. Right? This guy is estimate the y star given d eta, where d eta is a whole decision, k-dimensional vector, while this one superscript 2, we don't care about A1. Okay, we only care about decision at D2. Okay, so we only care about decision D2. So this guy, so then this guy is actually estimate of this way. So you can see the difference. The difference is that here you have basically you have a y star T1 eta and T2 eta, right? So in k equal 2, T1 and T2. But here, we don't care about T1 now. We just leave whatever the given, observed, and just care about T2. Okay, so that is the kind of objective function we want to optimize. So you use this one to optimize. That actually will give you a best. So we optimize this one, and then plug in, and optimize with respect to eta 1. Okay, so T2 first. So try to make a single decision sequentially in a backward way. Okay. So if you do that, this is basically this is you know, two decision rule. Okay, that is IPW. Now we'll apply the same idea. AIPW. Same thing, right? So you basically have a superscript 2. So basically this one is that we only care about A2. Okay, decision 2. So basically we just leave A1 as a history given. So that basically is that this guy, so this one is actually 2. Is a doubly robust estimator of the A1, Y star, A1, and T2. And then optimize. And then plug in and optimize with respect to eta 1, D1. And then now the question is how to compute D1, Q1 under different choice, right? Under the optimal choice of D2. That is the Q-learning that I explained. So the idea is you need to create an impedance. You need to create the pseudo outcome under A2, under D2 optimal. And pseudo outcome under D2 optimal is nothing but the imputation under the different universe, right? Under the different regime. And then use that as a kind of outcome and fit the usual regression model. Then this guy will fit the this Q1 will be the conditional expectation of will fit this guy, right? Conditional expectation of Y star on D2 optimal. Okay, so that is the basically idea. classical analysis is the same as before, so I will skip it. So that's all. I don't know. But yeah, I'm happy to answer any questions. Well, if not, we'll meet in the next week. So there's no class this Thursday. Well, anyway, I'd like to thank you all for your active participation.
Thank you.